Good afternoon and good morning, everyone. My name is Magdalena Marszałek. I am in technical sales at Zurich Instruments, and today I will be your host during the Zurich Instruments webinar. This time, we are going to talk about impedance analysis. Dr. Tim Ashworth will present our MFIA Impedance Analyzer, showing its performance with two very different measurements. Before that, here's a quick introduction. I introduced myself, and Tim, let me also introduce our company, Zurich Instruments, located in Zurich. We have one mission. We want to provide best-in-class dynamic signal instruments for advanced R&D laboratories. Our portfolio consists of lock-in amplifiers able to measure on frequencies up to 600 megahertz, systems for quantum computing, and last but not least, impedance analyzers, MFIA. So, what can you expect in the next hour spent with us? Let me briefly tell you something about MFIA itself before I hand over to Tim, who will present the instrument and push it to the limits, measuring fast and low. The MFIA was released way back in 2016 when we saw there was a need in the market for an instrument which could cover a wide frequency range, including the elusive low frequency. In addition, typical IAs at the time were limited in the highest impedance they could measure. And they were also pretty slow to measure a single data point, so any quickly evolving signals could not be captured. We changed all this by building the MFIA based on our market-leading lock-in amplifiers. We avoided the traditional auto-balance bridge, and thanks to this refreshed architecture, we could open up the frequency range, impedance range, and vastly improve the single-point measurement time. I should also not forget about the software Lab 1 that we developed from scratch, allowing you to fully control your setup. You will see a lot of Lab 1 today. Tim will present two case studies showing the two highlights of MFIA, measuring fast and low, well, actually in the reverse order. So measuring low, you will see how to achieve precisely and accurately very low values of inductance and resistance. Measuring fast, you will see how little time MFIA needs to collect data from a single point. Are you ready? Here, I just want to ask you to actively participate in this webinar. Please submit your questions anytime using the QA box. We will answer as many questions as possible after each of these two demos. But I promise we will come back to all of you with all the answers after the webinar. Now, I will hand over to Tim.
Thanks, Magdalena. The MFIA covers countless impedance applications. Today, we'll be presenting two very different impedance measurements, which allow the unique features of the MFIA to shine through. Specifically, we'll be demonstrating measurements of equivalent series inductance, ESL, down to the nanohenry level, and equivalent series resistance below 1 milliohm. After that, we'll change direction and show you how the MFIA can be used to measure impedance very fast, below 10 microseconds. So let's start with the low ESL and low ESR. A great component on which to measure this is a commercially available DC link capacitor, such as this one. I'll give a brief introduction of what the DC link capacitor does, and then we'll look at why low ESR and low ESL are so important. Then, before we jump to the live demo, we'll have a look at the capacitor details and the specification sheet, as well as the fixture that we've used to connect the capacitor to the MFIA. So, what do DC link capacitors do? DC link capacitors have many applications in DC conversion systems. They sit between the DC source, such as a battery, and the three-phase inverter stage. They serve to reduce ripple and filter out transients due to the switching of the inverter. A good example is their use in electric vehicles. It's very important that these components have both a low ESR and a low ESL. State-of-the-art components have been developed with ESR below 1 milliohm and ESL on the nanohenry level, such as the component we're measuring today. But let's start with ESR. Why is this important? Any unwanted resistance in the circuit will dissipate power and cause heat loss, not great for confined enclosures such as electric vehicles. So choosing a low ESR component is key. Similarly, with the ESL, this is a parasitic inductance which would cause voltage overshoot during switching. So therefore, low ESL is also desired. Let's take a look at the component that we're measuring today. It's a 120 microfarad version, and it has 3 connector pairs. The spec sheet shown here specifies a low ESL of just 15 nanohenry and a low ESR of 0.8 milliohm. These are the parameters that we're going to confirm today. In addition, it specifies a tan delta of 5 times 10 to the minus 4, which we can also confirm with the MFIA during this demo. To fix the component to the MFIA, we use a custom fixture which has connectors which fit the connector pairs of the capacitor. We then use the user compensation feature of the MFIA to define a measurement plane at these connectors. We'll use the short compensation only, as this is most important when measuring at low impedance. The short component that we use is a PCB-based component, and it gives us a very good approximation of zero inductance. So now let's jump to lab 1 to run the measurement. Here you see lab 1, the software user interface of the MFIA. This is the default view when you open up the MFIA, and it shows an impedance analyzer tab with a sweeper below. The sweeper can be used to sweep frequency, test signal, or DC offset. In addition, it's configurable, so you can move the tabs to wherever you want to have just the right signals that you want to show. Furthermore, you can pull up a settings file so that you can configure your instrument exactly how you want it, which is nice for multi-user labs. Before we start with the ESR and the ESL measurement, let's quickly confirm both the capacitance and the tan delta of the component. So first we need to connect it to the MFIA, to the fixture rather. Then we open up the plotter. We set the frequency to 120 hertz, which matches the frequency at which the tan delta was specified. So here we see the green line. This is the tan delta because from the drop-down menu, we've selected delta and series capacitance. So let's measure this using a math tool, cursor area. You can see here that the measurement at 120 is 1.6 times 10 to the minus 4. So that's well within spec of the spec sheet of this component. Now we switch to the second trace. The red trace is the capacitance. I'm going to double click on this, and you'll see that the vertical scale now changes to capacitance. And here, if we measure across, if we average across a couple of seconds, again using a cursor tool, we see that the value of the capacitance is 121.894, and you can see it's stable to 3 decimal places. We have a standard deviation of just 1.5 nanofarad on this measurement. So measuring at a fixed frequency gives you a very precise and accurate measurement. So let's stop that there and move back to the sweeper. The first step is to do a short compensation. So we'll add a short component to the fixture. And then we open up the compensation tab and we select short only compensation. we can run that directly, and the instrument runs through the frequency and builds up a conversion table based on the short. So now it's already 50% through, it's completed, and it's transferred to the instrument. Before we do anything else, we should confirm that when we now measure this short, we see a real Z very close to 0. So now we'll sweep from 100 Hertz to 5 megahertz. We'll measure the real Z, and we can confirm when we measure across that whole range, we have a nicely centered 0 real Z, which has a standard deviation of around 50, 45 microohms around 0. So now let's look at the inductance. We can add the inductance. So we're now going to retake that using series inductance. We can remove the real Z, and we can add the inductance. Now let's take a shot. Perfect. And now you can see that the inductance of this device also looks pretty flat at this level. Let me zoom in. Double click to zoom. There we go. And you can see it above, let's say 10 kilohertz, we get a nice flat value. At 5 megahertz, we get just 2 picohenry as our inductance baseline. So this gives us a very high confidence that when we measure something above that, we're going to get a nice, accurate result. So now we can move to measure the component. Plug this in. The first set of connector pairs U. And we run over the same frequency range. One difference we will make, we'll increase the number of points. 200 points. And let's look first at the real Z. The real Z corresponds to the ESR of this component. So here we go we don't need the cursor area tool. So let's double click here, and there we go. We have the ESR of this component is now measured. We can see it over the full frequency range from 100 Hertz to 5 megahertz. And we can see that at its lowest point, 2.9 kilohertz, we get 781 microohm, which nicely confirms the datasheet of 0.8 milliohm. So now we can measure the second connector set. So we can hot swap that and retake the same sweep and see how the ESR compares. These connector pairs correspond to different internal capacitances, so they will show some difference. You can see here at 18 kilohertz, we have a low of 742 microohm, which corresponds to the ESR. Let's take the third pair for completeness. And through symmetry, the first pair and the third pair should show the same behavior at the higher frequency. So there we go. It nicely matches the first pair. So let's now have a look at how reproducible this is. So we can zoom in here. And in the history tab, we know that this one is our connector to U, so we can label that. Now we can remove that. We can go back to connectors U and retake to show the reproducibility. So we take a single shot without making any other changes other than disconnecting and reconnecting. And now you can see here that the difference between these two measurements In fact, we can measure that. We can use a cursor tool, tracking area. And we can see the difference between these two measurements is just 20 microohms. So that's the reproducibility of this measurement. It's very high. So now we can move on to the ESL of this component. Now, as it happens, I already have that stored. So now we can just double click on here and we can see the ESL of this component. We can add all three of these. And we're just going to look at the inductance above the self-resonance. So that's above 150 kilohertz. We can convert to the log scale and we can now see the inductance of this component. So the equivalent series inductance. There we go. And let's focus on connectors U. And you can see that we measure in three different places with three different measurement tools. Peak 1 gives 19 nanohenry at 171 kilohertz, 15 and 11 at 745. This confirms the ESL of the component, as they don't give a frequency at which it was measured. So you could take, for example, a measurement here at high frequency. Let's add the tracking tool. We measure that here to be some value here. Let's use a different tool. Perfect. You can see that it's just 8 nanohenry. So we've confirmed the ESL there. And we've also confirmed that it's very reproducible. So there we have it. Let's summarize what we've measured in this demo. We started by running a short compensation routine to set the measurement baseline and to define the measurement plane to the characters of the fixture. We measured the baseline and saw very low levels of around 50 microohms and 1 picohenry. This is well below our desired measurement level, so we have confidence in the result we've measured. Then we measured and confirmed both the ESR and ESL to be within specified values of the datasheet. But what's more, we measured this over a wide frequency range and measured how the ESR and ESL change with frequency. And finally, we also demonstrated very high reproducibility when disconnecting and receiving. So that brings this demo to an end. Now we can move to the questions and answer session.
Tim, thank you for the first part of the presentation. It is fascinating. These low values are indeed impressive. I am sure many of our users or future users would appreciate the sensitivity of the MFIA. I can see that we have been flooded with questions from our audience, and our technical team is doing their best to prepare the feed. I can also see that you're setting up your lab one to have it on hand. Are you ready to start, Tim?
Thanks, Magda. Yes, I'm ready for the questions.
All right. So let's start from a question from Mary. How can you save the data from lab one?
Right. So let me go back to the sweeper view. And here, let's say you've taken the taken your sweep, and then you can either save it as text, so directly from this view, or you can save it as, for example, vector graphics. So essentially, you can get the CSV, or you can get the vector graphics, which you can then put straight into a report or edit in a vector graphics program. You can also export as PNG, and then you can also export it in MATLAB format and HDF5. HDF5 is a great format for Python coders, and it has the advantage that you can reload your data directly back into Sweeper if you want to compare measurement with a historical measurement.
Okay, I think you explored all the possibilities. And I have another question for you from Krish. Is it possible to measure the dissipation factor of a capacitor?
Absolutely, yes. So we did that during the demo, but let me just show that again. I'm going to use the plotter tool, and then I'm going to select from the equivalent circuit model. I'm going to select the dissipation along this. And here you can see in the plotter, we're measuring at a fixed frequency. Again, it's at 120 hertz, which was the specified frequency. And you can see here in that would be the red trace. I'm sorry, the green trace. The green trace here is the dissipation factor of this component at 120 hertz. Let's crank that up to 1 kilohertz. There's a little bit of a step response there in the plotter. So we can get rid of the first trace. That has changed it significantly. There we go. After it settles, you can now see that we're measuring the D at 1 kilohertz, and it's increased significantly. It's now 6 times 10 to the minus 4.
Wow, that looks pretty cool. So thank you for this additional demo. Next question is from Tim. So he wanted to know more about the measurement accuracy and at what frequency ranges are these accuracies valid?
Right, great question. The MFIA has a basic accuracy of 0.05%. But of course, this isn't valid for all frequencies and for all impedance values. But we do have one of the largest sweet spots where you can get this value. And it goes right up to 500 kilohertz in frequency.
Okay, great. Thanks, Tim. And the next question is from Rob, whose work often requires traveling. And he would like to know how easy it is to use the MFIA in the field.
Oh, right. Well, that's an unexpected one. The MFIA itself is very small. It's a half rack width, and it weighs just under 4 kilos. In addition, it has a joint power supply, so you can either run it from the mains power or from a battery. So if you need to work in the field, you can run it from a 12-volt 2-amp battery for several hours at a time.
Yeah, this is pretty compact. That's true. So that was more sort of hardware question. I have a software question now. So is it possible to control the MFIA by any APIs?
Absolutely. Let me show you a typical example here. So we offer and support 5 different APIs: Python, MATLAB, LabVIEW, .NET, and C. What's quite nice, though, at the bottom of the Lab 1 window here, we have this log button. Here we go. And this essentially has logged every single mouse click I've done on the interface, and it's logged it in Python code. So you don't need to go into the node documentation to pull out the node names. You can actually write a script based on this. And that's toggleable between Python and MATLAB.
It's really great variety and can allow all of our users that have preferred language to choose whatever they are most comfortable with. And I have another question, this time about the maximum impedance that can be measured. Can you tell us what it is?
Absolutely, yeah. Today, of course, we were looking at the low end of the scale. We were looking below 1 milliohm, but the MFIA can actually measure up to 1 teraohm at the low frequency end. This would be very useful for anyone looking at dielectrics or insulation.
Great. Yes, you're right. We covered the low, but yeah, it's good to also mention our high value ranges. And now I'm afraid I have to stop this Q&A session on the low ESR ESL part in order to have enough time to show you how to measure fast phenomena. Please take your time, Tim. It is only the MFIA that has to be fast today.
Thanks, Magdalena. In the previous measurement demo, we saw how to use the MFIA at low impedance to get precise and reproducible measurements. Now we turn to a very different type of measurement where we look at changes in impedance on a short time scale. It shows that even though the MFIA can measure fast, it still maintains high precision to allow for small changes in impedance to be resolved. We'll start with an overview of the applications which need fast impedance measurement, and then we'll look at the fastest possible measurement time of the MFIA. And finally, we'll have a look at the setup before starting the live demo. So let's start with the why. There are many applications where fast impedance changes give critical information about the system or device under test, but they all have one thing in common: faster is better. A common technique which requires very fast impedance measurements is DLTS, Deep Level Transient Spectroscopy. This is a technique which can give information on the type and density of defects in a semiconducting junction. But there are many other areas where fast impedance measurements are required. For example, fast capacitive voltage measurements, sensor characterization, haptics, and microfluidics. So just how fast can the MFIA measure impedance? Well, it depends on the test frequency. At 1 megahertz, which is a typical test frequency, for example, for DLTS, the MFIA can measure in 10 microseconds in a continuous mode or 1.5 microseconds in a gated transfer mode. So the device under test today is a small, simple red LED. We've chosen this because with a DC offset voltage, we can change the capacitance by an arbitrary amount. We even use the MFIA itself to produce the DC pulse. We produce here at the auxiliary out, and we feed it to the auxiliary input 1. And now a word on the setup. We solder the LED onto an MFITF carrier, and we've inserted this into the MFITF fixture. As I said, we've produced the DC offset here. We feed it into the auxiliary input in, and we add it to the test signal on this connector here. And for accurate triggering, we send the same pulse to the trigger on the back connector of the MFIA. Now let's jump to lab 1 to run the measurement. So for this measurement, the first step will be to sweep the offset voltage and have a look at the capacitance. So we've selected capacitance from the vertical axis group. And we're going to sweep from -2 to +2 volts. Let's take a single shot. And there we have it. We see that the capacitance changes as a function of DC offset. And for this demo, we want a relatively linear area. So we're going to choose arbitrarily 0 volts, where the capacitance is 28. And we're going to measure at 1 volt, where the capacitance is 40.9 picofarad. So now we've decided on a suitable pair of voltage values. We can set up the MFIA to produce these values itself. So we're going to open up the threshold unit, and the threshold unit allows us to configure enable and disable states with an arbitrary time. We're going for a 2 millisecond enable followed by a 500 microsecond disable. We then feed this signal to the auxiliary tab, where we can scale this and produce the voltage amplitude as we wish, which is 0 and 1 volt. This is then fed physically from the output 1 into the input 1. So now let's take a look at the plotter. Oh, I missed a step. In the lock-in tab, we need to add this to the AC test signal. And while we're here, we can also adjust the current input, set that to auto, remove any existing offset. And there we go. The auto range here. We can optimize the current input range to 100 microamps, so we get the best possible signal. Okay, it's not going to work. Let's go to 1 milli. Great. So now we're set up. We can have a look at our signals on the plotter. Let's start with the DC offset voltage. So here you can see nicely that we're getting pulses. If I pause, grab the mouse, we can stretch that up and have a look at one of these. These are our pulses, and we can use a math tool, tracking, to measure these. So you can see at the top of the pulse, it's 1 volt. And at the bottom of the pulse, it's 0. So that's one signal. And let's now look at the capacitance. Double click here to scale. And let me zoom in to have a look at a single pulse. There we go. So the blue line is the DC offset. The orange line is the capacitance. Depending on which of these traces is highlighted, the vertical scale changes accordingly. So let's now have a look using the tracking tool. And we see nicely that we're at 40 picofarad at the top of the peak and 28 at the bottom, which nicely matches the quasi-static measurement we took earlier in the sweeper. The strength of the plotter is to view it in real time and to set up your measurement and optimize the parameters. However, to acquire real transient data with timestamps and the ability to trigger, we use the data acquisition module. The data acquisition module is a time domain tool which allows a particular number of points. So let's say, for example, 1,000 points. And let's say we want to look at the same two parameters, so capacitance and DC offset. We take a single shot, we force, so we don't trigger, and then let's have a look at the results. Here we go. So the blue is the offset, and now we can see the green is the capacitance. Again, we can add tracking tools, so we can read off the values. We can confirm that they match those values from the sweeper. And again, there we go with the 40 and 28. A key advantage of the DAC module is its triggering capability. Why is this important? For a clean transient like this, you can get all the information you need from a single shot. But if we repeat this measurement with a very small change in capacitance, the transient will become very noisy and some averaging might be required. And for averaging, you need to be able to trigger a very well-defined place. So let's now go back. Instead of using 1 volt, we just use 1 millivolt. So now what we should see is a very small change. Let's go to the history, remove this one. Here we go. So now we see a very small change in capacitance. It's almost not visible. It's within the noise. But if we go to the grid and we say, let's average 10 times. And we do a single. we need to trigger on trigger in 1. My mistake. And there we go. So now I'll just repeat that. And you can see, if we just remove these two, let's take another live shot. And now you can see that the initial shot in the DAC is then averaged with 10 different ones, and you can see nicely now you have your measurement. And now we can use a cursor tool to measure the difference in capacitance that we measure here. So we have 40 here and 40.1 here. And we can see here that the delta between these two is just 23 femtofarad. So that's a very small change. And with further averaging, you can measure down to the femtofarad level. So now we've shown you the resolution of capacitance. But we also want to look at the time scale. So let's now go back to the 1 volt to get a nice clean transient. And in the data acquisition, we can go back to a single measurement. There we go. In the history, we can just remove the previous one. Let's look at the capacitance. But what we want to look now is how quickly are we measuring? The capacitance itself looks very nice at this scale, but let's zoom in and measure how quickly we can track the change in capacitance. So there we have one vertical cursor. There's the second. We can turn off these. We don't need those for now. And we can see that essentially we're able to measure this change in capacitance in a time scale of 10 microseconds. So this is the fastest that the MFIA can measure in a continuous streaming way. But we also have another nice feature. We can use what we call gated data transfer mode, where basically we add another gate, which is here, trigger in 1. Let's add that to the vertical axis group. And take a shot. And now you can see that this gate will allow us to transfer data only during the transient. There we go. I'll double click here. Nice. So the gate, the orange line, defines the time or the period where we're going to transfer. And now in the lock-in tab, instead of transferring the data continuously, we can set to send on a high trigger. So there we go. Set that. And we go back to data acquisition, take a shot. Pause it. There we go. Okay, so you see there's some missing data, but it's indeed just taking the transient. But one important parameter to change now is we're no longer limited by the continuous data transfer rate of 107 kilosamples per second. We can dial that up to 856 kilosamples per second. So we're gaining a factor of 9. Now, if we repeat the test in the DAC and in the history, we can remove all the old traces. Now let's have a look at our transient. We have a single transient this time because the number of points is fixed, 1,000, but we're transferring that at a much faster rate. So now let's look at our transient. We can see straight away that it's no longer a single point, but we're actually measuring. So let's look at the capacitance, increase the vertical scale. We can see that we measure the whole transient in 10 microseconds like before, whereas previously it was 2 data points. Now we have much more data in there. And now we can just, if we zoom in a little bit, we can make out one data point. And we can go to a second one. And between these 2 data points, it's just 1.6, 1.5 microseconds. And that's the absolute limit of the transient measurement. So I think we can wrap up the second study. We've used several modules today. We've used the DAC module, the plotter, the threshold, and the auxiliary. We've shown that we can measure at the femtofarad level. We can measure a change in capacitance of, let's say, 20 femtofarads, possibly lower with averaging. We've also shown that we can add the DC offset voltage using the instrument itself, and we can show that in the same data set. We've shown that in a continuous streaming way, we can measure on a time scale of 10 microseconds, and we can then use the gated data transfer to increase that to 1.5 microseconds. And finally, we also shown that using the triggered acquisition in the DAC unit, we're able to average many different transients to pull out even smaller changes in the noise. So that wraps up the second demonstration, and we can move on to the question and answer session.
Great job, Tim. Many thanks. The measurement speed that you demonstrated in the second part is incredible. Perfect for materials which are pretty ephemeral. You want to probe them quickly to capture their unique properties. MFIA, when used with such a mastery, can truly bring your research to another level. Thank you, Tim, for sharing this knowledge with all of us. Okay, so let's move to the second round of the Q&A. Are you ready to answer some questions on this part of the webinar, Tim?
Absolutely, Magda.
Let's start with this one. Is it possible to observe the current and voltage signals?
Absolutely, yes. Let me jump to my lab one. I'm now sharing the data acquisition screen. So here in the vertical axis group, you can simply add the current signal. So that would be the D mod R signal, which corresponds to the amplitude of the current. And then once you acquire and take another shot, you see that now the orange trace corresponds to the current. I will add a tracking tool, and we can measure that directly. So let's remove the other traces. We don't need those. And let's look at both. Let's look at just the capacitance and the current. And you can see the red trace as it goes from 41 down to 28. The current is dropping from 109 microamps down to 74. So I think for anybody interested in current transients, this technique would be a very nice tool, especially since the time scale is the same. You can still measure below 10 microseconds.
Let's stay in this fast realm of measurements. John wants to know if these fast measurements can also be applied to resistance or inductance.
Yes, you're free to choose any of the parameters here and measure in exactly the same way. Naturally, you want to make sure that you're at a frequency that's suitable for the parameter you're measuring, but yeah, essentially inductance, resistance, they can all be measured in exactly the same way at this time scale.
All right. Next question. What is the highest offset voltage the impedance analyzer can provide?
Today we've been measuring in 2-terminal, and at 2-terminal you can add an offset voltage of up to plus and minus 10 volts, and that includes the test signal. So they have to be within that limit.
All right, I see. Now, Enrique wants to know if it's possible to perform multi-frequency measurements.
Yes, the MFIA is it can be expanded without returning the instrument, and it can be upgraded with an option called the multi-demodulator option. With this, it expands the number of demodulators to 4, which, to cut a long story short, means you can measure impedance at 2 different frequencies simultaneously on the same input channel.
This is a pretty unique feature, and I love that you can get this option very hassle-free. Now let's move to another question from Antonio. Can you connect the instrument to a probe station for on-wafer transient time test?
Yes, absolutely. Typically, DLTS would be done in a cryostat, but the MFIA can, of course, be connected to a room temperature probe station. It would be recommended to work with passive probes, and you would need either 2 cables or 4 cables, depending on whether you're looking at 4-terminal or 2-terminal measurements. But the functionality should be relatively plug and play.
Okay. Next question I have for you. What is the highest capacitance that MFIA can measure in this transient mode?
Okay, so we were using a 1 megahertz test signal frequency, and at that particular frequency, the limit is going to be around about 100 microfarads. If you wanted to go to higher capacitances, then it would of course be possible, but the test signal frequency would likely be, you'd need to reduce that down, but of course this would be no problem, and you might not achieve the 10 microseconds, but it would scale nicely at the lower frequencies.
And then the follow-up question from Surya: what is the highest frequency at which the capacitance can be measured?
That's going to be 5 megahertz. That's the upper frequency of the MFIA, and at this level you can measure from 1 picofarad down to around about, let's just quickly check my chart. Yeah, down to about 1 nanofarad.
Okay, great, thank you. Can you control external devices such as light source or temperature controller with MFIA?
Yes, we've got the analog outputs, which could be used to drive or at least to control a light source. So, for example, if you wanted to do DLTS instead of using a DC offset, you wanted to use a varying light intensity, you could directly put that analog output into your light controller. We also have a DIO, a digital input output board, which you could use to interface with other external instruments.
Okay, thank you. Can you also measure very long transients?
Yes. So today we were looking at the fastest possible transient measurements, but it's absolutely no problem to essentially sample at a much lower rate, and then you can acquire data for up to 12 hours. So in the plotter, for example, we would have a setting here up to 12 hours, and that would give you the ability to get those very slow transients and make sure you're back into a steady state. It's possible to go even longer than that if you use an API. With an API, you'd be able to stream the data indefinitely, as long as your host PC has enough memory.
Oh, that's great news. That's really fantastic. Another question: can we observe other parameters while sweeping, or does it block the instrument?
Let me demonstrate. Let's go to the sweeper. Essentially, you're free to add any. So what have we got here? We've got the absolute Z here in the blue trace, and we have the phase in the orange phase. So essentially, no, you can add as many of the parameters to the sweeper as you want. You can then, once they're in the sweeper, you can decheck them. That means they won't be displayed in the sweeper, but the data will still be there, so you can pull that out later. The same when you go to save that sweeper plot as graphics or as text, you can choose which of those traces you want to include. If you want to add a parameter, then you would need to retake the sweep, and it just adds it into it.
Wow, Lab 1 is really powerful. Unfortunately, this was the last question we were able to answer live. I can see that we still have quite a list to go down with. And for this, I would like to thank you, all the participants, for your interest and engagement. Let me quickly summarize what Tim has presented to you today. He measured precisely extremely low values of ESR, resistance, and inductance with excellent reproducibility using our user compensation feature. In the second part, the very fast capacitance transients were measured with high resolution in time and capacitance value of 40 femtofarads. We are very honored and happy to receive so many questions from you. Tim answered as many as possible live, and we will answer all the other you have submitted and share with you in a separate blog. You will all receive it soon in your mailboxes. You can always contact us directly with your impedance questions. You can find our emails here and in the speaker info tab. Get in touch and challenge us. Thank you, Tim, for a wonderful hour spent with MFIA. Thank you, IEEE, for hosting us. And thank you, in front of the screens, slowly finishing your cups of coffee, for being with us. See you in our next webinars.